It is 8 a.m. on Sunday morning, so that can only mean that I'm awake to hang out with my brother. Hey Eric, what's going on?
Hey,
So we're going to be working on some game that you've been building for a little bit here. How about you give people a quick intro for what we're going to be doing, and then we'll just get into hanging out and working on whatever code you want to write today.
well, basically we're just coding in Unity. I'm pretty new to it. Last time, me and you started up a new quad-based program. So just a basic quad in the background, but slapping some textures on it, trying to make a 2D flow simulator. So this is pretty much how far we got last time. You see some elements up in the top left. We have water, steam, lava, dirt. Heat will be this time. And you can go ahead and put those on the screen. Steam rises, water sinks, lava sinks a little bit more slowly. They're all various different colors.
Lava's really not
Uh,
really affected by gravity. It's
yeah,
fine.
and it doesn't have to be. In the background are basically just a lot of shaders. That's the world shader. This is the heat shader, which hopefully we'll be working on this time.
Cool.
Height, flow, they all have the basic same structure to them. And of course, the main script where it's a giant .c file that isn't very structured, but meets my needs.
Hey, it looks good to me. So, and you're
Right?
being you're being generous here. So, when we left last time, we had something that kind of functioned, and then you sent me a little video the next morning that was like, "Hey, here's what I did," and it was most of this. So, I mean,
Okay, fair enough.
yeah.
Maybe worked out a little bit in between and forgot where exactly the cutoff was, but
Um,
yeah. So that's where we are with the various elements, and now I want elements to interact because it's great
cool.
that okay, I have water and I have lava, but when lava touches water, you think it would make some steam.
I
Uh,
see. Wait, is are lava and I'm looking at this here. Is lava resting on top of water? Is that what's going on there?
So because they use the same type of shader,
Yeah.
water and lava don't actually behave differently. They're just rendered different colors. So if you
Hmm.
have water first and then you put lava on top of it, the lava will sit on top. But if you have lava first and then you put water on top of that, the water will sit on top.
Oh, gotcha. Okay.
Yeah.
It looked like you were doing some sort of thing with densities or I don't know, something like that.
Maybe for a future, but
Yeah, one complication at a time, right?
exactly. So
All right,
in
cool.
any case, this should never happen in the game because this
Yeah,
would evaporate into steam relatively quickly.
yeah. Okay. Man, that looks really cool. So, yeah, I'm really excited to work on this. Okay, so we're gonna be working on heat transfer. So what have you done on heat transfer so far?
So I prepped for this session a little bit.
Oh,
I've
nice.
got a basic heat shader. If I go to the project menu here, I have a heat material and a heat shader, just like we made for the flow, the height, and the world rendering.
Right. And
Will all
remind
have
me,
materials and shaders.
the world one is it puts together all the different like it's the compositor. Is that how we set that up? I forget.
Yeah, because you need one world rendering
Hmm.
texture, the world shader takes all of the other things, put them together, and the actual world rendered texture is what gets put on this quad.
Gotcha. Okay, cool.
So in under the hood, we have the main script, and we have our initialization section,
Hmm.
our
Whoa,
make
you
things flow
okay.
section,
Make things flow
uh,
section. Got it.
our solids section, which currently is just dirt
Yeah.
because solids don't need to flow.
Okay.
I've implemented a little bit of a heat section,
Hmm.
which compiles all of the textures from above, and then the height, the world renderer, and the update long section, which basically all it does is it's responsible for when you click a number up here, it
Hmm.
changes that number, and then
Oh, I
when you
see.
click, it places the element. That's what the
Gotcha.
update section does. The rest is done by shaders.
Cool. Okay. Looks good.
Yeah. So the
That's
heat
easy.
shader
Hmm.
that we currently have is toggled on and off.
Thanks.
Uh,
Thanks for making that bigger.
yeah, we're all gone. Uh, and And currently, all it does is sum up every other element.
Hmm.
So it doesn't use itself, but all of the water, steam, lava, and dirt, it just averages them here, puts it in the red channel, and then in the world shader, if I turn it to black and white plus heat, which is this section here,
Hmm.
it takes the average of the elements that were in that and then adds yellow as heat.
What is average of elements? Is that the average heat?
So
Oh
the
no, that's the
average
average.
was, yeah,
That's
the
average
original
presence of
colors.
elements. Okay.
Yeah, so the
Okay.
more element there is, the harder the color it is, which is this RGB section here.
Hmm.
But in black and white mode, um, these are now yellow because yellow is just the amount of water plus steam plus lava plus dirt in that spot. So
Got
heat
it.
isn't actually an element here,
Hmm.
and it never will actually be an element. But
Right.
just to prove that, okay, yes, the inputs are working,
Yeah.
here it is.
So in this that's why right now there's because there's no heat, there's no change from that. Is that correct?
Uh, exactly. So the heat shader only just sums up everything else.
Hmm.
If we change this to this pixel red is this pixel red, or just simply don't do anything,
Yeah, got it.
um, then what this will do is just maintain basically
Hmm.
position.
Maintain position? What do you mean?
Anything that was in that spot in that pixel will stay in that pixel.
Oh, okay. For
So water, steam, lava, and dirt are now just black and white, and heat is yellow and just stays in place.
oh, you were actually able to add heat as an okay, I see what you're doing. Okay,
Yep.
got it. So then
So
so heat is its own map. And
yep.
okay, and so you want to propagate heat based on what other elements are around.
So
Is that right?
heat heat is like an intrinsic property of whatever is placed. It shouldn't
Hmm.
actually be able to be placed by itself.
Right, but
Uh,
you need to do this in order to well, you're doing this for debugging.
Essentially, to
Yeah.
build it up, it's much easier to start with being able to place heat.
Yeah.
Um, and what it should do is it should not exist if there's not an element there,
Hmm.
uh, but is a property of the element so that if the element moves, like water, as it
Yeah.
flows down, the heat needs to go with whatever particle it's latched onto, essentially.
So
And
you're not doing radiant heat then.
well, and not only that, not only does it have to flow with the element,
Hmm.
but when that element is near something that is a different has a different temperature,
Hmm.
which is like heat divided by amount
Yeah.
for simplicity in this game.
Yeah.
It needs to flow either to or from that other element.
So what I'm saying is so you're not doing radiant heat, you're only doing conductive heat, which
Aha, yeah,
makes
no, it
sense.
doesn't travel through space.
Okay, so it doesn't travel through space, and yeah, materials have to be touching in order to transfer heat, which
Yes,
okay, that makes things way easier.
right?
Yeah. Okay, cool. So, but this seems like it should be pretty simple. So, have you tried implementing any piece on this yet, or are we just gonna
Uh,
do this live?
I did, and it failed miserably. Uh,
Okay, well, that's always a good place to start.
right? Basically, so I went down a fork and tried to implement heat into the height map layer because in the height
Okay.
map layer, or in the height shader rather, you already
Hmm.
have all of the inputs for water, steam, lava, and dirt.
Right.
And so I made it into a toggling like A/B buffer like the other ones.
Right. Okay.
And then because we only use the red channel here,
Hmm.
I used the green for storing temperature and the blue for storing heat. So heat was calculated first, and then you divide by the amount, you get temperature. And all of the
Okay. Right.
calculation for heat transfer was in there.
Yeah. Is, is temperature okay? So, forgive the question. I'm forgetting physics here, but is temperature useful for us? Like, can we just do all the calculations in heat and kind of ignore temperature?
No, you do need temperature. So because each element has a different heat capacity,
Hmm.
um, if you have 10 heat in the first block and you have 10 heat in the second block, but you have 1 kilogram in the first block and 2 kilograms in the second block, the 2 kilograms are actually colder.
Right. So they are colder. Shoot. Okay, hold on. So they're
And
colder,
heat
which
will
means that
flow
heat's
with
going
the
to
temperature
flow.
gradient.
Oh, heat flows with temperature gradient, not with heat gradient.
Yes.
Okay, so well then same question but inverted. Can we just store temperature and do we don't care about heat?
Um,
Just for
a good
simplicity.
question.
I don't know.
A good
I don't know how the
question.
math works. So
Neither do I.
so because I know that like in it literally works using heat, but
Yeah.
it might be easier if we just consider temperature since that's the thing that gets manipulated and then we don't have to like maintain this other value. But I don't know if there's anything about
Yes.
like I don't know, two materials in the same location having different temperatures but sharing heat. Like is
So
that
they will not, for simplicity. Everything
okay?
in one grid unit
Hmm.
will have the same temperature.
Oh, thank goodness.
Right, because
Okay.
that's the other one. For those of you that didn't know my life in the past, I tried implementing this not in Unity, and
Oh, that's right. That
basically
was
the temperature could flow between every element in the same box and every element in the surrounding boxes, which is like n to the nth. It was not good.
was that was that in Lua? Was that game?
Yes, yeah, that was
Okay.
in Lua.
Yeah. So not only was it interpreted, it was also like crazy hard or crazy amounts of computation going on.
And everything
So
was stored in hash tables because Lua.
right, yeah. So I mean, come on, that's what programming is. Like you get a job in the programming and like in coding industry just by saying the answer hash table to just about any question. Like like seriously. Every interview question is just like, oh, you should use a hash table. Like, okay, thanks.
That makes sense. Those things
Yeah,
solve everything.
yeah, exactly.
It's like
Um,
VLOOKUP. Excel interview, VLOOKUP.
yep, VLOOKUP. You just gotta know VLOOKUP. Yeah. Pro tips.
So we're here in the heat shader.
Yeah. Okay, cool. Yeah, let's do this. So everything's the same temperature. So the heat shader is I mean, really a temperature shader, I guess.
We can call it temperature.
Okay.
Well,
Well, we
oh,
can
right.
keep it
So
heat so
the
you don't
thought
have to.
experiment.
Yeah.
We have 2 kilograms at the temperature of 10 degrees. So we're going with Celsius here.
Mm-hmm.
Um, actually, we should really do Kelvin because then it's absolute.
Oh,
So let's say 300,
okay.
and we have 1 kilogram at 100 Kelvin.
Okay. Got it.
Can we mix those and know what the
And know which one's which.
final resulting temperature would be?
Hold on. You said they're wait, oh, one was at 100 Kelvin?
One is 100 Kelvin, the other one is 300 Kelvin.
Okay. I mean, yeah, we
Assuming they
can
all have the same heat capacitance.
yeah, well, if they have the same heat capacitance, then that's easy, right? Because then you just take the proportion.
Yeah.
But if they have different heat capacitances, then I mean, then I think you have to use the total heat thing, where it's like, okay, so you back up into heat, and
Hmm.
then you shoot, it gets more complicated if you have three elements. Because each one's
Well,
just gonna be
so
so each one's gonna have a proportion of the total heat, right? According to their heat capacity.
yes,
And
meaning that they're
then
all the same temperature.
right. So yeah, so you just need to get the total heat capacity, and then you take your heat capacity and you wait, but they're all just gonna be the same temperature. So why does this matter? Because
Well, so if half of the left-hand one flows into the right, what is a new temperature on the right?
so it's remind me, left hand one is 300, right hand one is 100, and half of
Yeah,
300 half of 300 flows into 100. So and half
but
by mass, not by temperature.
yeah.
Okay. Uh,
Well, so the left-hand
hold on.
one is still 300.
You know what we should use here? You know what we should use?
What? We should use
Just
mind map.
uh, drawing is not currently possible. Hey, give you the ability to whiteboard. We should we should we
What?
should whiteboard it on your screen here.
Why is whiteboard not possible?
I don't know.
Whiteboard on.
Whiteboard on. Okay, here we go. Okay, so we have yeah, let's do this. So we have
Nice.
300. Uh, Kelvin over here and 100 Kelvin over here.
Uh,
Did I
uh,
type? 100 Kelvin over here. And this one over here is going to be what? You say 3 kilograms?
Sure.
All right. And this one's 1 kilogram?
Sure. Yep. So they're
Okay.
they're both
So same,
proportional,
right, same heat capacity, right?
assuming they're the same heat capacity. Yes.
So we want to flow this way.
Hmm.
And we're going to say, so what is the resulting, well, the resulting heat always has to end up being balanced, right?
No.
So there's, no, they do, because because if you stick two things next to each other, they're going to come to the same temperature, regardless of
But
what they're made of.
in one time step.
Right, right. So so eventually they'll come together. So whatever formula we come up
Yes.
with needs to, if it's iterated, result in that. So
Yes.
it's almost certainly going to be a proportional step between some two values in here, right?
Yeah. Hmm.
So, and it's going to be based on Kelvin, or sorry, it's going to be based on temperature because it has to be.
Hmm.
Uh, and heat transfer is, wait, heat transfer is, are we doing the thing where heat flows faster with a larger temperature gradient? Probably, right? Because that's just the way things work.
We can.
Okay. So,
It's probably how it will turn out anyway. It's like how the water flows faster with a larger height gradient.
mhm,
It just happens that way because of the math.
cool. So, I mean, what if we just set a constant? Like we just do it exactly like water.
So if we do it exactly like water, um, temperature will temperature will even out. That's
Hmm.
true. Over, let's say you have an entire row of these, because two dimensions are easier.
Hmm.
That entire row will have the same temperature in the end. Let's say that this one, so upwards is temperature, left and right is physical.
Right.
So if this one starts out at a high temperature,
Yeah.
it will look like this for a bit.
Hmm.
Like if it's just a point temperature in the middle, it'll look like that,
Yeah.
and then eventually even out,
Yeah. It'll eventually
uh,
just flatten,
the
just like
water
a
does.
fluid. Yeah. Yeah.
Yeah.
Is that not right?
That's correct. That the temperature will even out.
Hmm.
Um, but if this block here has a much lower heat capacitance,
Hmm.
then temperature will flow much faster through this. And if this one has a very large heat capacitance, heat will flow much slower through this.
Oh, I see. So that's the thing that we need. We need some sort of control over the transfer rate through this.
Yes,
That
because
is
the whole
actually,
idea of implementing heat isn't just point to point. It's so that you can have a barrier
hmm,
with a thermal connection like copper, and then
right.
this will be isolated essentially, and that will be conductive,
Yeah.
or at least at a much faster rate than this one
Hmm.
is.
Like they'll still heat up through, it'll still heat up through here. But
Yeah,
yeah,
eventually.
right. Okay. Got it. So I think then there's two pieces to this, right? There's delta T, right?
Hmm.
And then there is some constant, let's call it K. No, K is bad because we already have a K. Uh,
Yeah.
let's just call it X
Hmm.
because it's transfer. So an X is the time step. So and delta T is well, okay, yeah, delta T is definitely change in temperature. We're going to use delta for time. So because you see what I did here? XD XD is this is going to be the amounts. So there's this, which is per time step how much heat gets transferred, right?
Yeah.
And
Hmm.
then there's also uh, based on how much change in temperature there is, how much gets transferred. So this value should be less than one, and then we just multiply those two things together, and that's how much gets transferred. Does that seem right? So like,
Could we try it out
yeah. So
with this example here?
yeah. Okay. If you so if x is low, like the heat transfer is low. Let's say it's okay, so 300 minus 100. Let's just do some, back of the napkin math here. So 300
Hmm.
minus 100 is 200. So is delta T. And then let's say x is, I don't know, x needs to be less than 1, which is that true? Okay, so the reason that this needs to be less than 1 is because you never want to transfer more than your delta T in temperature.
Yes,
And in
because you
fact,
can't.
right, because you can't. And that in fact you actually don't want to transfer more than half your delta T.
Also true, because half would be equalization of the two temperatures.
Right. But then it even gets more complicated than that because if you're transferring in other directions, then you don't want to take so much temperature from something that it just doesn't exist anymore. Have you solved this problem already for flow?
Um, so
Remind me what's going on here.
I solved this problem for heat
Hmm.
actually in a way that I thought worked, but
Right.
it
Oh,
ended
this
up
is taking proportions of it, right?
yes.
Okay. So, well, hold on. So, what I'm thinking is that there's a minimum amount or there's a maximum amount that we know to transfer is safe because if it only transfers in four directions. So,
Yep,
as long as you don't take enough from, oh, this is gonna be tricky
it's
because
1/5.
it's 1/5. As long as you don't take more than, well, no, but you're doing it simultaneously.
Yep.
Right.
So
Oh, so it's 1/5. Yeah,
in the flow shader
yeah.
with our lovely pictures overlaid,
Yep.
um, we calculate our flow northeast southwest,
Hmm.
and then just flow that amount. What it's divided by in here is the flow divisor,
Right.
which is one of the properties set, and that flow divisor is minimum 5. So for
Is this how you get things to flow at different rates?
exactly. So for
Uh,
water, the flow
mhm.
divisor is 5 plus the number of flows plus that, and for
What's the number of
lava, it's
flows?
25. So the number of possible flowing elements. So
I
um,
see.
it's just that.
Okay. So
It's
we can
just a number that seemed good.
we can kind of do the same. Yeah, I mean, we can kind of do the same thing for heat, right?
Yeah. So the way that it was solved, or that I solved it for the other for first implementation of heat,
Hmm.
was you know that you have one element flowing in four directions, assuming that they're all in or flowing heat in four directions.
Hmm.
Assuming that they're all equal, that's exactly 1/5. But
Right.
you have to multiply that by some stuff. So if you have a element with a high heat capacitance, it'll go faster, and if you have a low heat capacitance, or sorry, low heat capacitance, it'll go faster, and high heat capacitance, it'll go slower.
Oh, so what we're
Um,
what we're actually doing is the 1/5 where that comes from is the fact that you were flowing equally in each direction.
well, that you could possibly flow equally in each direction.
Right. So so yes, that you could possibly flow equally in each direction. So
Hmm.
what we need to do is um, we need to take the sum of the transfers. Man, it's really hard to write with this thing because it's writing with
Yep.
lag. Okay,
Yeah.
so we take the sum of the transfers and
Hmm.
then we say that is the so that's the total transfers. So we're just gonna call that, like, let's say T, and then sorry, the sum of the transfer capacity, because like so what I'm saying is with flow,
Mhm.
So this looked like, your box, and then you had one, 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 and one, because you could
Mhm.
flow in each direction. Sometimes one of these was zero, right? But
Yes,
because
but
you,
in any case, it didn't dynamically adjust for that.
right. So in this case, so now we need to dynamically adjust for that.
But what?
Well, we need to, because we need to know what the or how much can flow in each given direction. So for heat,
It would it would be 1/5 times some stuff, and so the maximum here is 1.
I don't understand what you're saying.
So if as long as we constrain this to have a maximum of 1, then you could
Hmm.
say the maximum heat that will flow in every direction is 1/5 of whatever that amount is.
I see. Okay. So yes, but so this is the piece I think that is what we need to look at,
Okay.
because there's some amount that's going to be left over in the unit from which the heat is flowing, and we have to make sure that the temperature in there is no less than any of the temperatures in the adjacent cells. Does that make sense?
Which you can do by multiplying by the temperature gradient.
Multiplying 1/5 by the temperature gradient.
Well, so working the temperature gradient into this box.
Oh, I see what you're saying. All right, let's try it. So,
So
yeah.
the equation that I got for heat transfer, I'm not sure if it works for temperature transfer,
Hmm.
was 1/5 times the average heat capacity of the cell that it's flowing to.
Hmm.
Um,
Average capacity of all elements in that cell.
yes,
Okay.
times this cell's average, uh, mine, I guess,
Hmm.
prime,
Yeah, sure.
uh, which so and capacity is less than or equal to 1,
Okay.
right?
Is one high? Like one is
One would
maximum?
one would be the maximum flow
Okay.
or maximum flow of heat.
Right.
So no, if it's like half, then yeah,
I
it
see.
would flow slower.
Got it.
So multiply those out,
Hmm.
and it starts decreasing and decreasing and decreasing, right? So you have the average capacity of the other one, multiply the average capacity of this one. That will make things that flow slowly not give away heat too quickly, and things
Hmm.
that will heat up slowly not take too quickly.
Right. That looks good.
So we do that times. Um, now we have to know how much to transfer. Uh, so that's T final or T target minus T, I don't want to say initial, but me,
Hmm. T
T
prime.
prime, T subscript with T superscript. It's great. This is good math.
Yep, this is great.
Um, so that's the change in temperature, but
Yeah.
this is greater than 1.
Uh,
So
right.
uh, we have to do the percentage difference,
Hmm.
and
What?
then
Okay, hold on. So finish.
so once we have the percentage difference,
Yeah.
we have to make sure that this is not positive, or if you put it the other way around, it's not negative. So you always want to calculate heat in one direction.
Hmm.
That's either flowing all in or all out, because the next cell here that does that exact same calculation
Right. It's gonna do it the other
has to come
direction.
out with the same result.
Oh, yeah. So if you have a cell that's both getting heat in and heat out, yeah.
Yeah, but they'll never occur in the same direction. It'll either
Right.
be flowing this way or flowing that way, and they both have to have the same number.
Right. They both won't flow into each other. That doesn't make
Yeah,
any sense.
yeah.
Okay.
Yeah.
So
So the
yeah.
proportion times
Hmm.
the capacities, but I'm not sure if this works with temperature.
So why does it need to be a proportion? Why not just not divide by T prime?
Because then here, this goes to 1,000, and now you're doing 1,000 times 1/5, and
Right, but if
you
it
don't
goes,
have that much temperature.
why do you not have that much temperature?
Because, or so if this is outflowing.
Hmm.
Let's see. Let's just do it here. So this one
Yeah,
is
yeah.
at 300 degrees.
Hmm.
This one's at 100 degrees.
Yep.
So this is 200 divided by whatever, and so 200 would flow from here to there.
Wait,
Times divided by some stuff.
this
Will
is,
that always work?
I mean, this is the opposite direction, but yes.
Yes. So right, t
Yeah,
prime minus dt. Let's do
yeah,
that.
yeah. Okay, cool. So
We
yeah,
got
I
we
think,
got an eraser here somewhere.
eh, I think that this works
Okay.
because so if you have because it's a delta of 200, right? And then you multiply that by a fifth, so there's the like if we're doing absolute heat or sorry absolute temperature. So
Absolute
the
temperature.
lowest
Yes.
that it could possibly be anywhere else would be 0, 0, and 0, right?
Yep. Yep.
With a average with a capacity of 1 to flow in each of these directions,
Yes.
right? That's the worst possible case for doing this,
Yes.
which means that each of these you'd have a 300 delta, but it'd be 300 times a fifth, so that's 3
Which
fifths
is the
of
normal flow,
300,
which is the
which is the
same
normal
problem as the
flow,
flow problem.
right? Which means that the flow to here is strictly less than that amount, which means that we're fine.
Hmm.
So we're conserving heat in this universe,
Which is good.
which is good. So I don't think you need to divide by T prime. However, what we will need to do is represent temperature using a float on the range of 0 to 1.
Yes. Which is not a
So
problem.
which means that this is absolute 0. So this
Hmm.
is absolute hot for our universe.
Yes. Indeed.
So we'll pick I guess you'll pick an absolute hot and then adjust your temperatures to match, I guess.
Yep. Yeah,
I,
everything basically just has a divisor on it, and that
mhm,
divisor is just the resolution of
right.
how much you can have.
Yeah. I think this is gonna work.
Okay.
So
Then we
let's
can go ahead and get
let's
right
do
into
it.
it.
Yeah.
So here in our heat shader, we have water, we have steam, we have lava, we have dirt.
Cool.
For the simple case, we're not going to worry about actually flowing elements, which means we just need to know what is in that box.
Hmm.
Or maybe we don't even need to know what's in that box. I don't know yet. I haven't thought that far ahead. And what do we do with
Well,
these elements?
so you need to know, I mean, so this is you're doing heat flow out, right? Like everything pushes out. It doesn't come, you don't do heat flow into your location,
Sure.
right? So, okay. I mean, I'm asking, like with the flow version, you did it as you always deposit or like deposit flow. You don't
Yeah.
draw flow.
So
Okay.
this strategy
Yeah.
um, is you always only have a north and an east flow,
Hmm.
whether they're positive or negative. You only have a north or an east flow for the element.
Oh,
But
interesting.
heat itself, um,
Huh.
yeah, we can either do all out or all in or something like that.
So that's a clever optimization. So can we do the same thing here, or does that not work?
Um, Again, haven't thought so far ahead.
Well,
If we have a temperature,
hmm,
it has to be able to flow to the left and to the right.
hmm. But we're doing the
And
one
so we
fifth. We're doing the 1/5 thing though.
Yeah,
So,
but we do have to calculate in every direction.
hmm,
So in the flow shader, it does calculate all of the flows, whether they go out or in, because it has to,
okay.
so that you maintain, because the one on the right
Oh,
will
right.
calculate a negative and the one on the left will calculate a positive, and they'll both modify themselves to match.
Got it. Okay.
But in terms of the actual flow that was recorded,
Hmm.
uh, is just north and east.
Oh, I see. So got it. Okay.
Yeah,
I see. I see what you're doing here.
yeah, because that's
See,
relevant for the second stage, which is heat has to flow with the element that just moved.
right. So I'm going to, Hmm. I'm wondering if that's actually true.
If
Well,
what's
let's
true?
if you have to flow heat with the element, like
So,
if you're fine with heat being one frame behind, it might not matter
hmm.
because heat might just like if you start the oh well, I guess then if you like lava on the first cell that it like if it's moving, if lava's moving, then the first cell that goes over would have no temperature, and then you'd have to flow into it, and you would actually be losing heat continuously as you're flowing. Okay, yeah, you're right. You do need to do flow.
Well, so the idea that I always have for, well, maybe I don't have to, is you have a stream and
Hmm.
you drop a piece of lava into this flowing stream. It should
Right.
not flow upstream
Oh,
if it's going fast enough, right?
yeah, you're right. Yeah, the heat should not flow upstream. All right, fine. So
Yeah,
yeah,
well,
let's do the easy version first.
yeah. So this is just pure spreading of heat, which will stabilize over all of the relevant objects,
Hmm.
like essentially a flow that is bounded to the edges of um, the elements on the screen
Yeah,
instead of being free flow. So how does it work? This pixel is heat.
temperature.
Starting heat. Starting temperature. Temperature. Then the let's
Nice.
assume the heat capacity of everything right now is just one.
Okay, you can
So
use
that takes
stand-in variables for it, right?
yeah, but it'll uh, it'll make the beginning easier. So it should just flow in every direction all the same.
Okay, cool.
Um, and then we will need to calculate this pixel's up, down, left, rights, which I can just steal from here. Or sorry, north, northeast, southwest. To say,
Looks good.
okay, the temperature above
Hmm.
and this pixel should get some stuff. Um, so that's the temperature difference.
Hmm.
And then what do we want to do with it?
So we wanted to say what's the difference times the difference in or times the multiplied average heat capacities, heat transfers, and
Right,
then times
which
what
are
the
all ones for now. So one
right.
fifth times the temperature difference to the north is how much is going to flow north,
Yeah.
because this this cannot it can be negative.
Hmm. Wait, what can be negative?
This can be negative.
Yes, it can. So it's max zero in that, right?
Well, it can also be positive.
Right. So that's what I'm saying is the temperature flow north is going to be max of zero and whatever you calculate.
Uh-huh. But like the flow, this one will need to subtract temperature or add temperature depending on what flows from the top unit or what transfers to the top unit.
No, I thought we were only flowing heat in one direction. Isn't that not true?
Hmm.
So
Hmm.
like if this is hotter than the next cell, then it transfers heat
Yes,
into the next cell. If the next cell is colder than us, then it doesn't do anything.
but it would need to increase in temperature somehow because you can't.
Right, isn't this going to increase it in temperature?
I can't
Oh,
set
right. You
another
can't
a
set the
different
other.
pixels.
That's right. Yep. Yep, you're right. Okay, so
So this is just the temperature
yeah.
difference,
Yeah. Okay.
and this is ending up a lot like flow.
Yeah, this
Actually,
is yeah, you might just be able to copy pasta here.
it's let's see what this is.
Yeah, what is all this?
So we take the maximum of the minimum of the. No, let's take east west,
Hmm.
because the north and south have the flow gradients, which are
Oh,
how gravity, quote unquote, gravity works.
Gotcha.
So this is the simple version. And so the flow to the east is the east minus this,
Mm-hmm.
and the minimum of this to the east divided by
What?
the flow divisor. So the height difference here is essentially the temperature difference,
Yeah.
and this pixel's amount is the minimum amount that could flow.
Is the minimum amount that could flow. I thought that was
Or
only
so
defined by the
you have
temperature difference.
well, you have to take the minimum because you can't flow more. So if the temperature difference is 200
Mm-hmm.
and you can only flow 100, that's not going to work.
Right, but
Remember, there could be multiple elements per square. So this is the element
Mm-hmm.
transfer. So
Oh,
it's
this is
possible
for,
that the height is
yeah.
bigger than this element's amount.
So I mean, that's possible for flow, but I don't think that's possible for heat.
True. So this temperature difference,
Yeah, it just replaces the
uh,
min.
let's make this east because we're working on east.
Sounds good.
Is this, and we don't have to worry about it being greater than the current because
It can't
there
be.
is none.
Yep.
Can't be.
And then, okay, so flow divisor, that'll just work. And we
So
don't
this
need the,
is plus the eastern flow,
yeah.
or assuming that the other cell has more temperature. And then this is this minus the other, which is the negative.
So, but in this case, this calculation is symmetric.
Yes.
So we
Exactly.
don't even need the second piece.
Yep. So minus negative, which doesn't matter. All this simplifies.
Yep.
Into that.
Don't you love deleting code?
That's great.
So it's like you have this big complicated expression, and then you're down to, oh.
Yeah. This divided by
Yep.
that.
Cool.
Which is, so the temperature difference divided by the flow divisor.
Mm-hmm.
Here we just have.
Perfect.
There you go.
All right. Cool.
So we
that in each direction.
simplify this down to here. And we could just do it east-west for now.
Don't forget to add parentheses again to your subtraction.
That is true. Very important.
Pair programming, yeah.
Hurrah! So we have our starting temperature, which we're putting here.
Yeah.
And then we do that variable plus flow east plus flow west.
Wait. Shouldn't it be minus? Hold on. Yeah. Wait, this pixel east minus this pixel are... Yeah,
So
it should be minus. It should be minus, I think.
We have this pixel and we have this pixel.
Right.
This has 120 and this has 100.
Break out my pencil here.
Yeah.
So
this pixel east.
So let's say this is the one that this is this pixel.
Yeah.
And this is east.
Yes. So east minus this is negative 20.
Yep.
Times 0.02, and then this adds negative 20. So already this is in the wrong direction.
So that's what I'm saying. So you should subtract the flow from the return.
Yeah.
Yeah. Because then this will go up in temperature.
And instead of a double subtraction,
you just want to flip the direction?
Yes.
You know how that works.
Yeah. So the flow to the east, if this pixel is higher, it will flow to the east, and then.
Yep.
Wait, no, this is still subtraction.
Hold on, what?
Yeah, I'm confused.
I'm confused too. Didn't we just draw this? Okay, hold on. If this is bigger than that, Yeah, still
So
subtraction. Okay, so hold on. If that,
because this flows to the east, you have to subtract it.
yeah, put it back.
But then how did? Okay.
Maybe I think I was just confused. Well, let's put it back this way. Okay, so if the pixel to
Because
the east is higher than this pixel, then this is negative. How is it still subtract? What is
no,
happening
this
right
works.
now?
This works. This works. All right, we're gonna make it. We're gonna make it simpler.
Okay, yes, let's please make
Uh,
it simpler.
Always referencing yourself.
Yeah.
If you are higher than the other one, you are
Hmm.
flowing a positive amount that way, which means you are taking it away from yourself. So
Okay.
these are all
Let's.
flows out.
Right. This is what happened. Okay. Got
Yeah,
it. These are all flows out.
which means this is minus. If we calculated
Yeah.
flows in, this would be plus.
Yeah.
So this is the all out, all in section.
Okay. Cool. So
So let's see what happens.
nice. Well, we should have temperature flow to the east and west.
Uh,
Whoa, bye temperature.
yeah, it looks like it worked.
Except that it
Uh,
went through empty space.
yes, because it's not constrained by anything yet.
Oh, right.
It's
I mean, but that's
just
pretty good. Like you end up wait, hold on, you end up with temperature bands, but why like why is this happening?
why is
On
what happening?
so like right here, you see above, it's going from one temperature to another temperature as you go horizontally. It should all even out.
Eventually, yes, but
Oh, you think it's just not happening very fast? Because like
the
it's
simulation is
clearly
only running 2,000 frames per or
second.
2,000 updates per frame, and then
Wait,
70 frames per second. So it's only running like 100,000 updates per second
only.
only, and so it'll take a while.
Okay.
Like you see, these are starting to even out the gradient.
Okay.
Everything is slow.
It looks all right. All right.
So
Cool. Well,
if
that's a
this
good
was
sign.
higher, maybe it would work, but I don't
Yeah.
know. So now that it flows, it needs to be constrained.
Hmm. So this is the maximum flow, right? So we need to multiply this by if we just use the heat capacities, like compute the average heat capacities and do that, then I think that just works, right?
Well, what if there's nothing in that spot?
Then the average heat capacity will be zero, right?
Okay.
Yeah.
Uh,
So you can just set them all to one right now.
Low, somewhat, high,
Also high.
middle. All right. So
Cool.
we have capacities. Great.
All right, sweet. So now you just need to sum up the amounts in each adjacent cell, right?
That's a lot
Wait,
of.
no, not transfers. Transfers come next, right?
How do I reference the? How do I know how much water is in the cell to the right of it?
I don't know. Don't you have that somewhere? I thought that's what the water texture was.
Yes, that's why in the water texture,
Oh,
I need to go to the right one.
oh, sorry. I thought that that was for flow, not right. So you have
It's
you have
all.
it's all of it.
It's also required for flow, but
Okay. So you have flow as two of the components and then current value as another component. Is that correct?
um,
Like RGB, so RGBA, what are you using those channels for in the water texture?
in the water texture,
Yeah.
I have R as the current value,
Hmm.
G is the northern flow, and B is the eastern flow.
Got it. Okay.
So
So you
thereby
so you need
taking
R.
the so taking the water
Hmm.
GB will tell me north and east,
Yep.
and taking the southern flows G will tell me this one's southern.
Yeah. Got it.
Yeah, but
Okay.
just to get the amounts, I need all of them.
Hmm. Yep. So yeah, you're right. So we just need the R components and that'll do it, right?
I hope so.
You gotta transfer these over to all
Figure
the
it
other
out.
elements.
Hop, hop. Steam, steam, lava. Right. So what do we need to do? Calculate what capacities?
We keep calling it capacities. I think that that's
It's probably not the right word.
not the right word, but it's because it's like it's flowability or like conductance. Maybe it's conductance. We should probably use the
Heat
word conductance.
conductance, conductivity. God damn it.
Conductivity, conductance, conductivity.
Yes.
Is that
Yes.
the
Heat.
word? That's the
So
word, right?
yeah, heat capacity
Okay.
is you add heat to it and it increases by that amount. Heat
Yeah,
conductivity is how fast can that amount flow.
right.
Correct.
Cool.
The
So like,
capacity is what I was using to calculate temperature.
that's right. So it's conductivity is what we need.
Mm, yes.
Yeah. Because like so I'm thinking about I just keep thinking about the what is it called? Those like the re-entry panels on the space shuttle. You know,
Yes.
the ones that you can hit with a blowtorch and get up to, 3,000 degrees or something and then just touch it.
Yep.
Yeah. Okay. So high capacity, low conductivity.
Hmm.
So
As opposed to copper, where you hold the end of a 1 meter stick and you put a blowtorch on the other, and you're like, ow.
yeah, exactly. Low capacity, high conductivity.
So these are conductivities.
Yep.
So here we're calculating the conductivities surrounding this pixel of heat.
Cool.
Which is just that. So do we need to know the amount
Here? Yeah.
like that?
Yeah. I mean, because you're gonna average all of these, right?
I don't know. Is that what we need to do?
Oh, I just think I realized something. So
Uh-huh.
we actually do need conductivity and capacity,
Uh-oh.
right? Because if you have like so if you just take the average,
Hmm.
then you would say if you have hold on, is this right? Okay. I think this will work, but I think we also need capacity.
Okay.
But maybe you can just bake it into conductivity. That's okay. So because I'm saying so if you just take the average, then a small amount of water and a large amount of steam results in a very high conductivity, which
A small amount of steam could be the same as a large amount of water.
you know what? Actually, I think that this is fine. I think that
Wait,
what we're calling conductivity is really conductivity and capacity, but
well,
because
so this is just the average conductivity,
mhm,
which is divided by here I have height.
mhm, height.
Yes. Because the height is the sum of the elements in these
Hmm.
before they flow. So I could either, I mean, I could just sum them up as well here, doc, 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 doc,
Hmm.
or I could just take height as a shortcut.
This is going to be a problem
But
if you end up with zero.
that's the thing, right?
Oh, I
So
see. So this is a weighted average. Okay, so
yeah,
this is doing a weighted average.
yeah.
Okay, I thought we were just about to divide by five, and I was like, wait, there's something wrong here.
Lol.
Yeah.
Yes,
Or divide by four. I guess that's the number of elements we have here. So okay, so there's a problem though with height being zero,
indeed.
because then your sum gets all out of whack.
So pretty much all of this doesn't. Oh, but then we have to do this for every direction
Hmm. This is true.
and check if the heights are zero in any direction and not do that.
So can we build this in a way that avoids having to divide by the height? So because the reason that we're doing this, so what are we doing with this value? We're taking the sums and we're just multiplying them together, right?
Hmm.
And if the height is 0, then necessarily all of these values are 0.
Yes.
So that means that the sum is going when we actually end up multiplying it down here, that's just going to end up being 0.
Hmm.
So it doesn't matter in the case of 0 what the height is because it doesn't do anything.
Yep.
In the case of transfer in a direction, so as long as one of them is non-zero, then you can add that, or you can.
That will give us the average conductivity of that element.
Yeah. I'm trying to see if we can if we can factor out the division by height somehow. So
I mean, you could do a zero check for height at the beginning.
you could, I mean, yeah, you can add a conditional to do it, but that's, I mean, conditionals and shaders aren't good. So,
Mhm.
you know what? Let's just write it and see what happens because it's going to be 0 divided by 0, which,
may or may not give you infinite. I don't know.
right, I'm going to look that up. Shader 0 divided by 0. I'm going to see what happens when you divide by 0 in a shader. The behavior is undefined.
Well, that's helpful.
So, so that's fine though. We can always, okay, what we could do is we could add a very tiny value to the height and make it always non-zero.
Hmm.
So, yeah, has to be plus though.
Right.
So, because then it's going to always be very slightly greater than 0, or whatever it's supposed to be. Which, however, that does mean that it can be greater than 1 now, which that would be a problem. Yeah, there's got to be the same value.
Oh, same, yeah.
Okay. Magic. I think that does it.
Hooray! Hooray!
So, yeah.
Wait, no.
What?
That needs to be plus. Otherwise, it couldn't be greater than 1. This can never be greater than 1.
Oh, right. Yeah, you're right. You're right.
But
okay, so that's fine. Okay, so I think we're good here. I think we're good because now we'll never divide by 0. We just have to do this calculation in every direction and for itself.
Well, so this is the average conductivity. But why are we doing this? So great, we have the average conductivity.
Because we want to multiply the average conductivities of the adjacent cell and our cell together.
Right. So we're doing that times average conductivity east times that.
Right. Times the difference in temperature.
Good coding practices right here, kids.
Yep. Don't try this at home.
Yeah. So we have east and west, and these are all going to be. We're just going to do it like this. Keep it neat. Keep it tidy.
So tidy.
Can't really do that, but whatever. It's fine. Hey, Mr. .r. Thanks, tidiness. This is east. So that is correct. And then the same thing for the west. Cool.
Nice.
Try it out.
Let's do it. So now if you add heat to the little dirt pieces.
Oh god.
What in the?
Undeclared identifier, dirt east.
Did you not add dirt east? You,
We
you
just
want to play
start
some League?
League of Legends here. We're gonna play some League. Oh god.
Perhaps
So,
later.
oh god. Stop. Northeast, southwest. Doing it. This is dirt with the dirt texture.
So it was funny. To actually do the stream, I
Hmm.
had to talk to people at work and make sure that everything was kosher and whatever. And
Yeah.
literally one of the only things that they said I had to do legally is put a little disclaimer on the profile that says that I work at Riot,
Ah,
because the
okay.
FCC says that if you ever talk about, so if they ever talk about League on stream,
Uh-huh.
then you need to disclose it. Otherwise, it's a what is it, an undisclosed endorsement.
Ah, yes.
And so they're like, yeah, we know that you're doing something else, but in case you ever accidentally say that you're going to play a game or
Accidentally
whatever,
just
or
start
your
League.
brother accidentally starts League and you mention it, it's like, oh, look what happened by accident. Yeah. So, yeah, glad I put that disclaimer on there.
Yep. Sometimes you just accidentally start playing League.
Exactly. So, oh man, just fell into it.
All right. Well, this is working correctly.
Yep.
We have heat in a void, and it is flowing theoretically, but at almost zero
Oh,
per
right.
second.
Is it flowing because we have the plus 0.00001? Is that why?
Um, Actually, no. I guess it is 0 per second because all of that is zero divided by
Right.
0.001
Yeah.
means it's zero times stuff.
Right. And because we were
So
safe, your shader didn't just explode by dividing by zero.
yes, do you want to try that? We can try it.
We should try that later. But yeah.
And if we put heat down here, oh, yep, there
Oh,
you go.
hey, that.
Yep, it spreads. Boy, does it.
What? Wait, hold on. Why did it spread in the void right there?
In the wood.
Oh, wait, that's right. Never mind. So I forgot you put down some material there. Okay, yeah.
Yeah, so it's oh
Oh, look at
Jesus.
that. Oh god, look at it go. Wait, how did it go? How did it go all the way across? Was there steam over there?
Should not have been. Very
Yeah.
interesting thing. Let's see what happens if we. Yeah,
No,
so it went all the way across to here.
well, hold on. So put like some heat over here, and then yeah, put some heat there, and
Well,
and
it's
then do it over
spreading.
here. How is it
It's,
spreading? There's nothing
I
there.
don't know. Is it 0.00001?
It might be a very small amount. I mean, okay, so now, so like yeah, throw some just throw some heat down, or throw
Oh
some
yeah.
whatever over here. Yeah, so okay, why is it like it's all the way over here is the heat, and then over here is the thing?
Huh. Let's find out.
Clear my little drawings, because I can't do it myself.
Clear the drawings.
Okay,
So
what's going
did I
on?
did I miss a no? It's probably that it is like just the smallest amount of element because the flow works practically the same way.
So it must be maybe heat
Wait,
just
but then what
flows.
triggers it?
Yeah, let's restart this. We're gonna do some investigation here.
So there
Okay,
can't be any elements in this box.
right.
It's an empty box.
Yeah.
So put some steam over here, put some heat in it. Whoop! It goes through the empty box.
It sounds like you're telling a magic trick.
I mean, it is magic.
See?
Magic heat.
Nothing over
How does it
here.
work?
Nothing up my sleeve. Heat transfers through the box.
Yeah.
Okay, yeah,
Um,
so
yep.
okay.
I'm super fast at that. There's a shortcut for that
For
pause thing?
pause,
Yeah,
the pause key, I think.
pause key.
Do you have a pause
Reason
key?
uses
Your,
that. I
your
have a
crazy
pause
keyboard?
key, but it doesn't work.
Oh, well, rip.
No, I mean it would, but huh, there we go. So that's what's happening.
Okay, so it's staggering. Do you see that? I mean,
Yeah.
unless it's just a visual artifact, it looks like
Well, I mean it's running 2,000 frames each click.
2000 updates.
Yeah.
It's a lot of updates, bro.
Yeah.
Okay, so it's definitely like I'm
but I
glad you're
don't
only
know
doing this
why.
in like one dimension right now, because that's making debugging easier.
Right?
Hmm.
Hmm. So let's assume you're on this side.
To the right.
You're an empty element and you're here.
Hmm.
This element has one heat, whatever, temperature
Yeah.
stuff.
Okay.
You have zero.
Yeah. Your
The
your average conductivity is 0.
true.
Which means you have no flow because everything is multiplied by your average conductivity.
Dang it. That is true.
Story's over, go home.
Stories ever go home. Yes.
So, so apparently that's not what's happening.
No.
Uh, what the?
Is height all right. Maybe I lied about height being a shortcut.
Well, that wouldn't matter though, because
Yes, it does. Oh God. Oh, I'm silly bean.
why? What's happening?
You
Is
can
height
flow
negative?
more than you have because this is the height of the east,
Uh,
and this is the height of the
okay. Well,
west.
that'll, huh. I mean, that'll do it a little bit.
Maybe. We'll find out next time on The Price is Right. With more free advertising.
I forgot to disclose that.
Uh-oh.
I'm actually Drew Carey.
Oh. So what happens now? We have heat. We have steam. Okay, nothing.
Yeah,
Hmm.
because that shouldn't have affected it. Because I mean, the main thing is average conductivity this for an empty cell should be 0.
Should be zero.
What if you just map average conductivity as heat for now?
Average conductivity this.
Yeah, just map that as heat. Do no
This
flow.
pixel r equals
Yeah.
that. Oh. That's interesting. What was I doing here?
I mean, we were flowing heat, right? That
Does that make a difference?
that probably makes a difference because it was probably the flow east. Flow east had more components in it, right?
I don't know. It's just this. Average conductivity east. It should be float. Oh God. Woo.
So it was setting what it was doing is it's setting all the values in there in the float 4 to that one float, which meant
Yes.
that it was doing something crazy. Okay, so yeah, that's probably was an issue.
Well, that's what you get for being careful while programming. Heat, steam. God damn it.
No, come on. I was so looking forward to that. Okay, yeah. Can
All
you
right,
just map average conductivity and like
doing it.
let's see what that is? Because if we
White
just get a
screen.
big yeah, if we just get big white screen,
Nope.
okay. So I mean, so that's good, right?
Yeah. Dirt, lava, steam work. Heat you can't see because it's not
Wait, why there's
doesn't
a
have any
weird little
conductivity.
box there? Did you see that? Or no, that might have just been a like screen sharing artifact.
Yeah, it's a screen sharing artifact.
Blorp, blorp.
Blorp blorp.
Okay, so that clearly
That's
works.
fun.
Okay,
So it is zero where it needs to be zero.
I mean, it clearly isn't.
What? But it was.
Well, I mean, it can't be though because, oh yeah, yeah. Just summing it all up, you're like here.
This should still be zeros, where it's not like so. That's all zero, and it's still zero.
Come on, why isn't this? So what I'm saying is it clearly isn't because otherwise there would be
Otherwise, it would work.
no capability to transfer heat. Wait, okay, so hold on though. Wherever you're showing heat is just R. You were getting blue in the heat transfer. What, right?
Sorry.
So go back and just do it the right way. Actually flow the heat. Comment that
This
out.
way.
Yep. Okay, so now go back into the program and let's test this again. So everywhere you normally do heat, it's yellow, right?
Mm-hmm. That's true.
So now drop that. See, it's blue. Why is it blue?
Probably because I'm not normalizing.
I mean, that's the
The shader, the world shader. I could do
or green, blue.
this.
The average is blue. Or so sorry, just the average is blue. Average plus heat. What is average again? Average is the average amount of stuff there, right?
The average is just the average color. So everything has a different
Average
color,
color.
and then it's so if I turn
Oh,
color
you're doing
on,
black and white plus heat. Okay, yeah.
yeah,
Yeah, then it does the color it's supposed to.
yeah, so that's color.
Okay.
And then I turn that off.
Okay, so it's black and white.
We see heat. Heat vision,
Heat vision.
which apparently is still blue.
Well, hold on. Red, green. Yeah, what the? Okay, hold on.
So
The
is
heat is, whereas
infinite?
heat is computed from the heat texture, which
Yeah.
in this case, you might be getting a divide by zero error or something. So the reason I say this, I mean, this is going to make it, yeah.
Question mark.
Maybe. But the reason I say this is because, so if it's blue, that means there's no red or green components.
Yes, true.
Are you in heat vision?
Yep.
Okay.
Is it flowing? Yeah, it's flowing.
Okay, so
Alright.
it must be that. All right, so
It's
yeah,
flowing.
go back into your shader.
Too
So
fast.
I don't think it's flowing too fast. So, but in the shader here, so we have, you must be having a small value divided by a just insanely small value. So like if height is 0,
Well, plus our 0.001, but maybe that's just too small.
well, okay, so but that should only be a factor, that should only ever matter at all if the height is 0.
Yes. And because float
And
math,
if the height is 0, then the average conductivity should be 0 even if it's divided by a small number, right? Like 0 over a small number is still 0.
I would hope so.
So what must be happening is the sum must be non-zero, but the divisor dividend, the dividend is 0. So the height texture, when is the height texture updated?
The height texture is updated after. Those clicks, do stuff. Right. So here we run the shader for flow of elements, which actually move the textures around.
Hmm.
Height is actually updated after
The heat
this
texture.
one, so it's not a shortcut for heat.
Right. There we go. So it's because
Everything is
because
perfect.
not a shortcut. Okay.
Not a shortcut.
So now small can be a small number. Yeah. And now it will not divide by 0. So hopefully heat will not flow across infinity in like empty space. You know, I mean, we just
Radiant
accidentally
heat.
implemented radiant heat.
Yeah, hey, look at that. Isn't that?
Look at
Oh,
that.
God, it's so lovely.
Oh my gosh, that is beautiful.
Oh!
Well, rip.
Rip.
Well, it was almost good, and then that happened. So
Yeah. Okay.
so we know what the bug is, at least. In some situations, the height
Up.
is just rip. Like,
yeah,
the height is not the
Okay.
height. So instead of sampling that texture, can we just add up the amounts? I mean, you already have them, so
We can.
it saves you a texture sample. kind of sucks, but I mean that might point to an issue actually in the height texture update. We should go check out that code probably. Like
Probably as
maybe
well.
it's missing summing one of the input textures.
Water, steam, lava, dirt.
Hmm.
Water, steam, lava, dirt.
Dirt, steam, lava, water.
Oh, right. That's why. God, you know what? I should never have put in height here.
Why? Oh, because it's divided
Because
by the
it's
number of
divided by the
elements.
number of elements.
So
Rip me.
that'll
Just
do
get
it.
wrecked.
Okay, well, not a shortcut. When a shortcut is not a shortcut.
In so many ways, not a shortcut.
Like,
Just
not only was it
every
updated not in the right order, it was also just not the number that you wanted.
every possible way.
Okay,
All right,
well,
small is small. This is manual. Good math.
yep.
Take me home, good math. Yippee!
Look at that heat flowing.
And then not because it's not able to anymore.
Yeah, it's just there's
Oh,
heat stuck in space.
be free, heat, be free.
Gorgeous. Look at that.
Lovely. It doesn't even cross a barrier, I don't think. Lovely.
Nice.
All right.
That's awesome.
That sounds like a commit.
Man, that looks good. All right, let's pause and take a break while you commit.
All right, sounds good.
Sound good? All right. Be back in a minute.